Good afternoon, everybody. I want to remind you that last time we ended the class by defining these angular coordinates, which we're going to use to analyze objects which are moving in circles. And we defined what we mean by an angle. The angle theta is the arc length s between 2 points divided by the radius r. So theta is equal to s over r. We can manipulate that a bit to get s is equal to r times theta. We have to use radian units for our angular measures if we're going to use these relationships. And we said, okay, if we have an object that's moving in a circle, well, a certain amount of angle goes by in a certain amount of time, and we defined omega, our angular velocity, as d theta dt. And we can relate omega to our linear velocity, which is in meters per second. The linear velocity is going to be the change in the arc length s with respect to time, ds dt. And using our relationship for our definition of omega here, we can rewrite that as the tangential velocity is equal to r times omega. And with these tools in our hand, these angular coordinates, we're now in a position to discuss the topic of today's lecture, which is velocity and acceleration in uniform circular motion. And our first order of business here is to define what we mean by uniform circular motion. It's not any sort of circular motion, but specifically uniform circular motion. And a particle is in uniform circular motion if and only if omega is constant. So if we have a constant rotational speed, a constant rotational velocity, a constant angular velocity, omega, or angular velocity, is a quantity like RPM, or revolutions per minute. It tells us how fast something is turning, and it refers to the entire rotating object. If we have a constant angular velocity, omega, a particle is said to be in uniform circular motion. So now I would like to direct your attention to the screen. I have here a turntable, and a turntable turns at a constant rate. This turntable turns at 33 1/3 revolutions per minute. And since we know that there are 2 pi radians in a revolution, that works out to about 3.5 radians per second for omega. And on this turntable, I have 2 particles drawn, a black particle and a red particle. And even though the angular velocity is the same, omega is the same for both the red and the black particle. Is the speed of the particle the same? Are the black particle and the red particle moving at the same speed? No, they're not, right? The black particle has to travel around a much larger circle in the same amount of time that the red particle travels around a small circle. So the black particle has to be moving faster, and we see that in our tangential velocity expression, which we derived last time. The tangential velocity is just equal to r times omega. So if r is bigger, the velocity is bigger, even for a constant omega. But in this situation, r and omega are not changing. So the black particle, it's at a fixed radius r. It's moving at a fixed angular velocity omega. And so therefore, it's moving at a fixed speed. Okay? Its speed is not changing. So if its speed is constant, is the black particle accelerating? Who thinks the black particle is accelerating? Who thinks the black particle isn't accelerating? Who is totally lost and has no idea? Well, that's fair. Well, for those of you who think the black particle is not accelerating, let me give you a hint, okay? I'm going to go ahead and remind you that velocity is a vector, and I'm going to go ahead and put a velocity vector here on the black particle, and we'll see that the velocity vector points in the direction of travel, and that the particle is traveling around the circle, and so this velocity vector just points tangent to the circle around the motion. So let me go ahead and put this turntable in motion again. And you will observe this particle in uniform circular motion, complete with its velocity vector. And what do you notice about the velocity vector? Okay, well, velocity is a vector, which means it has a magnitude and a direction. 2 vectors are only the same when they have the same magnitude and the same direction. And what is changing about our velocity vector here on the turntable? Its direction is changing, right? So the vector is not constant. If its direction is changing, then the velocity vector is changing. So let's go ahead and stop this for a moment, and we can agree that if the direction of the velocity is changing, then it must be accelerating. And so our next task is to determine what is the direction of that acceleration. So I'm going to go ahead and draw a circle up here on the board, and we're going to go ahead and look at the turntable that I have on the screen, and we're going to record some of the results from the turntable onto the picture of the board. So let's go ahead and start here with our velocity in this sort of horizontal position and pointing up. I'm going to go ahead and put this light green vector here that says v0 to remind us that this is where our initial velocity started. And if we allow the particle to continue in circular motion, at a later time, it is going to be around the circle a little bit further right here. And you guys should recall, since we've been doing motion diagrams for the past several weeks, that the acceleration is defined as the limit as delta t goes to 0 of the change in velocity with respect to time over the change in time, which is equal to dv dt. And this acceleration vector therefore points in the direction of the changing velocity. The acceleration vector is on the left-hand side, delta v is on the right-hand side, so the acceleration vector must point in the direction of the changing velocity. So in order to find the changing velocity, we need to take the final velocity and subtract off the initial velocity. So here is our final velocity here, and if we want to do the final velocity minus the initial velocity, I got to flip this guy over, so it's a minus vector, and so that's v final minus v initial, and that gives us delta v, which is this little orange vector right here that points along right here. V final minus V initial gives us delta V. So let me go ahead and record that here on our chart. We have our vector V final, and it is undergoing an acceleration that points in this direction, which is along the delta V direction. And we can repeat this process for a new vector. Let's say we start at the top, and this will be our V0, pointing horizontally to the left, and then we allow this to continue around its path a little bit here. Okay, if we're going to do the V final minus V initial, going to go ahead and flip this guy over, so it's minus, and V0 minus V initial, from where we start to where we end up, is this little vector right here, which points along delta V, and that is the direction of our acceleration A. So at the top position over here, we have another vector, points in this direction, and we have discovered that the acceleration points in this direction. And hopefully this convinces you that if we repeat this process at any point in the circle, we find that the acceleration points inward, towards the center of the circle. All of these accelerations point inward towards the center of the circle, which brings us to the conclusion that acceleration in uniform circular motion points towards the center of the circle. Okay, and is called the centripetal, which means center-seeking acceleration. Now, what about the magnitude of this acceleration? What is its magnitude? We know that the acceleration of uniform circular motion points in, but what about its magnitude? Well, let's go ahead and refer back to this diagram here. Let's say we have some initial velocity, which I will call v0, and at a later time we have some velocity v1, and we will say that this angle that is traversed is an angle d theta. Now, if I redraw these velocity vectors, over here we're going to have that v0 points up, we're going to have that v1 points to the right, to the left, and this angle d theta here is the same angle d theta that is going to be in here. And our change in velocity vector, our dv vector, is going to point in this direction here. And using our definition of arc length and d theta, we can get that dv is equal to v0 or v1, which have the same length. Since the speed is not changing, I'm just going to call it v. Is equal to v times d theta. I'm going to call this equation 1. Okay, and we also know that v is equal to the change in arc length with respect to time, which is equal to r times d theta with respect to time. So we have v is equal to r d theta divided by dt, or dt is equal to r d theta over v. I'm going to call that equation 2. Now, the acceleration is equal to dv dt, so in order to find the acceleration, we need to take equation 1 and divide by equation 2. So dv divided by dt is going to be equal to equation 1 divided by equation 2, which is going to be equal to v times d theta divided by r times d theta divided by v. The d thetas cancel, and we get that the magnitude of the acceleration is equal to v squared over r. V squared over r. So the magnitude of the centripetal acceleration is equal to v squared over r, or the full vector form of the centripetal acceleration is magnitude v squared over r and points inward to the center of the circle. And this is a key result of this course. This is an important result to remember. I'm going to go ahead and put a box around this, because this is at the center of all circular motion problems that we're going to be working in this course. Okay? Just like in projectile motion, the acceleration was equal to 9.8 meters per second squared, and it pointed down. It didn't matter if we threw the ball up, it didn't matter if we threw the ball over, it didn't matter if we threw the ball down. In projectile motion, the acceleration is equal to 9.8 meters per second squared, it points down. Now we're dealing with a different type of problem, circular motion. And in circular motion, the acceleration has a magnitude of v squared over r, and it points in. And it points in. In all circular motion problems, the radial component of the acceleration is equal to v squared over r and has a direction that points in. It doesn't matter if this is a ball on a string or a roller coaster on a loop or Tarzan on a vine. If an object is traveling a circular path, the radial component of the acceleration is equal to v squared over r, and it points in. This is something we need to remember. This is something we're going to use. It's something that we should not forget, that if an object is traveling in a circle, the radial component of the acceleration is equal to v squared over r, and it points in. Something we all need to remember. So let's go ahead and finish this up with an example. Your roommate is working on a bicycle upside down. He spins the 60 centimeter diameter wheel, and you notice that a pebble on the tire goes by 3 times every second. What is the speed and acceleration of the pebble?